to do. At the beginning of the of our first meeting of the second part of the class, we were discussing a strategic plan that combines together all sections, chapters that you want to cover within about 2 months, to have our effort logically organized and show the connections. We are still pursuing, we are not changing mind on a way, but what we are going to do today is related to this diagram, but it is a pale shadow of our big plan. So in some sense, like when I was building a diagram for the whole class, in the center we do have dissipative dynamics for electronic states, which provides the rates, dynamics, kinetics of the processes, such as charge transfer or light emission or just non-radiative de-excitation. In some sense, our today's meeting is related to it. So we are going to get result that belongs to the same category. We are going to get rate and population kinetics by much cheaper, simple, and inexpensive ways. And Fermi's golden rule is a good reference point to compare results of the of the dissipative dynamics that it is our top goal. We do have Hamiltonian, and our major application is light to matter interaction, although there could be multiple of other excitations applications. We are still within time-dependent perturbation theory. In the class, we do not go beyond first order up to now, but I hope to learn from you more about second and higher order in today's. And just a little note for London, who is, the book is here, who is going to present on the infinite order and time ordering. So this picture and its explanation are expected. It's a little side note, which I probably should remove from the whole story. When one has more than first order, second order perturbation theories, there are 2 times, T prime and T double prime, because there are more than one event of interaction. And then one considers all events of interaction between system and perturbation as a point in the 2-dimensional space. And there are tricks to exclude half of them, to make it at least half as easier by selecting a triangle. But for the details, I cannot wait until Thursday. Okay. So we are in the first order perturbation theory, and we do not have statistical thermodynamics today. We do not have thermal equilibrium. We do not have a true ensemble, but we will have some pale shadow, some reflection of this process by making summation of many final states. So there will be some summation, and as a result of combining these 3 arrows, we will get rates. So this will be not a full theory, but it is something that both theory and experimental community were practicing for almost 100 years, like 90 years, most successful, and it works in vast majority of practical applications. So tomorrow at Wednesday lab evening, we will add so-called rotating frame, which substantially shortens numerical effort if one wants to go to tiny details of a long time period of evolution, but it's not covered in today's meeting. So the goal is to get this rate population kinetics, and on the way of converting the solution of first order time dependent perturbation theory into this rate, we will do multiple boring exercises at the level of freshman and sophomore, calculus 1, calculus 2, but it's unavoidable to see the result we have to do. And I hope I will be able to complete everything myself. If I fail, I will ask help either to find errors or to come to the board, because I think the background material is inside your mathematical muscles. So each of you should be able to just take this plan and deliver today's lecture. It doesn't take any outside information. It takes only the last equation of our last meeting and few low-level derivations that are typically skipped from the attention if one is glancing through a thick textbook. Okay, I don't know where we would put the break, but hopefully a little earlier. But the last thing, after getting to the final result, I will use time to enjoy a little bit of math. And I don't know, would it take 5 minutes or 45 minutes, but at certain point in the derivations, we will need this integral. And I hope you'll be able to discuss how to get it. So if you know how to prove it, or you have some ideas, you can shorten our time in class and speed up things, either by helping me or replacing me. Okay. Any questions on the strategic plan of the meeting? I'm really missing the interactive style of taking interview from each participants, and we are close to it. Today's meeting is easier than previous two, and we are almost close to the edge of converting to a little more relaxed style. But maybe today, once again, I will do like solo presentation, but soon we will start being more interactive. So with your permission, I'm going to erase, because it's just a summary what we're going to do. So the last or second last equation from what we've got last time was first order correction to the population of state A as function of t. So we started from chopping Hamiltonian onto unperturbed and which is 0 and prime perturbation, which is time dependent, and then the solution was we were looking for solution in the format of summation of expansion coefficients in the perturbative corrections. So the first order correction that we have derived can be expressed as zeroth order solution in case there are no perturbation, and for most of the practical cases, we are not looking onto the states that are originally populated, and we drop this term. And then integral from initial time to final time matrix element that brings us to state K from state N, time-dependent perturbation, and here there is a zeroth order population of state K and accumulation of phase as time goes by. So we did attempted to apply this solution for the situation of quantized level of a molecule that is being subject of electromagnetic radiation, right? So we assumed that H prime is transition dipole electric field, and then omega t, and then we have obtained the solution of the first order that was containing two terms. The difference between frequencies and summation of frequencies. And if one works carefully, there should be some constants that I admit I do not memorize. So likely it's 1/2, according to the cheat sheet. Then we were looking that if we are considering the resonance excitation, the denominator provides selectivity. So if the frequency of the incident light is close to the transition energy or frequency of two levels, this term is maximized, right? And then we also expanded the exponential into Taylor series, and then we canceled these frequencies and found that it will be just linear growth independent of frequency, proportional only to the strengths of coupling between matter and light. This one is so far from resonance and can be dropped, right? Or some people consider emission as a process with negative frequency. When if omega is less is negative, then it comes to resonance and one takes this term into account. But for us simple guys, we will just drop this term and process forward. Okay. What was done last time and what we are going to do today? I'm not yet so retarded to repeat the same question and repeat the same answer again. I was just planning to look on it from different aspect. So last week we looked for initial state N, which is like ground. We considered K as our excited. We do have the Kn as their frequency, and we considered the transition facilitated by optical excitation with frequency omega with a little bit of offset. Omega minus omega theta. Right? So it's a like schematic diagram of what we did last time. What we are going to do today. And once again, the probability amplitude, first order correction, is found to be proportional to time in the first power, right? And the probability, which is amplitude squared, will be times squared, like same as what we've got in the Wednesday lab, right? Now we are going to modify the schematic diagram and admit that we can have not to scale that we have multiple states, k minus 1, k plus 1, so infinite or large number of states around. And we still do have excitation of frequency omega, and then this excitation will have slightly different offset which of each of the states, right? We are starting with initially populated ground state, but we are interested into the following process. How probable is that population of the ground state will be pushed elsewhere? Will be excited at all, no matter to which state. Average to the whole band. Like probability to excite a band. I am impatient to disclose the intrigue and the main result. So in the first situation, when we deal with only two levels, when there is only one final state, the probability of the final state, which is only one level, as function of time, is proportional to t squared, right? In this situation, probability of the final state, which is summation over states, will be proportional to t. So it will be, in mathematical sense, lower but constant. The rate will not change over time. And the main goal of all our efforts that I did try to chop off on little steps is just to prove this difference. So if we excite from one level to a multitude of levels, the average rate of transfer of excitation will be proportional to linear time. How to formulate it on the a little bit more rigorously and mathematically? Probability of all excited states can be summation over k not equal to 1 ck star ck, and they all are in the first order and they all are time dependent. And the probability that system will survive will reside in the ground state. It is 1 minus P of t, so 1 minus summation of k not equal 1 ct t k star 1 1. So we are going to take this expression, plug it into there, and mathematically explore it. if you would do numerical effort rather than derivation of equations, there would be nothing else. You just look on the consequence. But we are playing a game assuming that we do not have computers. Therefore, we will do like few derivations, and most advanced of them will be to take this integral, which, well, we are playing open cards. There is no intrigue, but let's try to get these things. Okay, so I'm going to slowly walk to the board number 3, and I will take first order solution from here and plug it into this expression. So we need to take complex conjugate, multiply by itself, and apply summation. So this is about an hour effort, but as a result, we are going to get just stuff proportional to time. Summation not equal 1, first C first. Okay. Before going to here, I'm going to rewrite it once again. So C sub K 1 minus I H bar mu E 1 okay or 2. And now I keep only E to the minus I H bar. Oh, I do not need H bar if we are already in frequency domain. Omega 1 T minus 1 omega minus omega T 1 plus complex conjugate, which we cancel and decline because of resonance conditions. So there are two ways to analyze this expression. One is to take complex conjugate and multiply by itself, and then identify that there will be 1 squared, this stuff by itself once again, and then the summation of these two factors, right? So it will be like 2 plus 2 cosine by Euler equation, and then cosine can be converted into sine for a little bit more comfortable processing. Another way to obtain comfort, I understand what we are doing here doesn't relate to comfort at all. We are making an effort against human nature, but shortcut, easy path to think about this expression is to assume that e to the power minus I omega t is a product of E minus I of half frequency. And 1 is E minus I over 2 omega minus omega t 1 t times E minus I over 2 plus omega minus omega t 1 t. So this is always permitted. So we just have a E A equals E A over half squared, right? And here we have minus and plus, which cancel and give 1, right? So if we plug these two things instead of exponential and 1, we can put the same factor outside of brackets, right? And then inside, so it's all set up to gain comfort. So we'll get complex oscillating thing outside, right? And upon complex conjugate, the stuff will cancel. This factor will cancel. And then inside the bracket, we will have a subtraction of exponentials rolling, accumulating phase in the opposite direction, which will be one of the trigonometric functions. If it is minus, then it will be sine. Okay, and then it will become, in some sense, a real function. So you can probably go right to the answer or just put a few steps more. Minus half of the frequency 1t, and then subtracting these two things with negative frequency being first, it will be minus 2i sine omega minus little omega k1 t divided by 2. So it will be half of the argument. Does it look reasonable, or anyone wants to catch an error, if any?
We have a coefficient of 2 out front. Oh, wait, yeah. No, yeah.
Because of Euler is like 2 exponentials divided by 2i for sine.
Yeah, because I think sine is exponentials minus each other over 2. So then
Over 2i for sine, and over 2 for cosine. Right. Okay. And then the C star first order k will be the same thing, where we flip the sign in front of any imaginary unit. Plus I h bar k1 the 2 e minus I plus I over 2 omega minus omega k1 t plus 2i sine omega minus omega k1 over 2 times t, several brackets. So if we do multiply this complex conjugate functions, we are going to cancel this oscillating exponentials, right? Because they accumulate phase in opposite direction, they compensate each other. And then, so I times I will be -1 times -1 minus another minus, and I times I -1. So it's -1 to the 4th power, which will be 1. So we likely we have a positive thing. So star C1 without star will be mu P1 electric field h bar squared 2 times 2 4 2 times 2 4 sine omega minus omega k1 divided by 2 times t squared.
Your dot product should also be squared, right?
Correct. And we do need to have a denominator, which I skipped here. Omega 1 omega capital minus omega lowercase k1. Right? So the word happy is not applicable. It's all against human nature. But other major concerns about this expression. or we believe we can go forward with it. And now you already see why we, as at our entertainment time for the last part of the lecture, we need to integrate sine square over of argument divided by argument. The only thing that separates us from practicing this integral is that here we have an argument of frequency offset times time, and in the denominator we have just frequency offset. So it's different variables, and you would need to bring it into agreement so that there is the same variable everywhere. So to get it the same variable in denominator, we will need to multiply and divide by t. And since it is energy offset square, we need to multiply divide by t squared, right? When we look at this expression, which is our original plan, we observe that there is a summation. And in case the levels are spaced very densely, very tightly, in a few steps, we will replace summation by integration, right? And then we'll see that we need to integrate of this expression where these different values of frequency will be offset between incident light frequency and different levels in our dense spectrum. Okay. No major concerns yet. So with your permission, I'm going to erase this board, and I believe I will be able to reproduce this expression just from the top of the head, so we can move into. So we did introduce transition from 2 levels to infinite number of levels. We did cancel the oscillating imaginary exponential, and we do have a summation over final states to get probability of generalized excited state. Now we need to revisit concept of density of states to do the transition from summation to integration in a reasonable way. I'm missing another chance for interview, but maybe we can briefly at least vote. Who feels comfortable with the concept of density of states? Who feels very discomfortable with density of states? Who is in the middle? Okay, so when most of you are doing electronic structure calculations, we are representing the levels of realistic materials by a concept of density of states, because they are so dense, and if one has more than 10 levels, it's hard for human eye to follow them, right? So there is an average curve. And there are notations for conduction band, valence band for occupation, the gap, right? And they are used either to assess ability of a material to conduct electricity, like if gap is 0, it is a conductor, or to assess the color of a material. So the gap is associated, if one converts the value of the gap into frequency and nanometers, one can assess the color that material will absorb and emit. So I'm going to skip a couple of equations, but if we take this, the density of empty and density of field of occupied states, so it is density of single electron states or orbitals. If one is looking onto transitions from occupied to unoccupied, one can set up the density of excited states. So the lowest transition will be from highest occupied to lowest unoccupied, and it will correspond to lowest available transition for the system. Okay, right? And if one multiplies this density of excited states by oscillator strength, one will get absorption spectrum, right? So density of excited state multiplied by absorption spectrum by weighted by oscillator strength gives absorption spectrum. If we set up, if we explore this density of state of a certain frequency, and if the states are dense enough, then ability of optically induced transition does depend on value of density of states in the frequency corresponding to in the range of energies corresponding to the incident frequency, right? So in the context of today's meeting, we will speak about density of excited states. And we will call it with letter N, and we can reset the 0 at the point of omega, right? So we just make another axis, maybe E tilde, and here the 0 will correspond to omega. And then we will speak about frequency of incident, or it doesn't matter what is the order, frequency of transition minus frequency of the incident light. So this notation refers to the electronic structure and absorption spectrum calculations that most of us are doing, and it will refer to how dense, how many states are close to the selected frequency. So why we need this concept? We are going to make a transition from discrete set of levels to a continuous distribution. What if instead of a molecule with or atom with 10 levels, we speak about nanostructure or continuous solid with number of levels close to infinity? Then individual level is not possible to monitor. We can speak only about the average density at a certain frequency, at a certain transition energy. Okay, so the next step would be to combine this concept of density of final states, because initial state is ground state, and this is density of final state, with our summation for and probability to go from initial to anywhere in the excited state. So we're done with concept of density of states, and now we need to do this limit. So I'm going to walk to the board number 3 and continue there. So I will keep this definition and the on the top left and derivation in the bottom right, and plug them in and use the concept of density of states. We can put no, we can put constant outside yet. So how do we practice transition from summation to integration? Right now, we assume that there is a discrete set of excitations, omega from ground state to state K. We should admit that this summation is equivalent to integral over range of energies times the amount of states in this range. I was not thinking deeply about it recent time, so if you have thoughts or questions or challenges, go ahead. If you don't, we just swallow it and go forward. But it is the same thing if the final states are very, very dense, very frequent. It is a standard thing to do. In case we know that there is a selectivity, in case the incident frequency is already set up, probably we are not going to go dramatically far from the center of frequency. So we can set up that it will be detuning will not be very far from the center, like omega a little bit minus delta, omega plus delta, relatively narrow range. Okay. There's word. If we want to do it very, very formal, we also need to do transition dipole being distributed and dependent, because you know the transition dipole is specific for each transition. It should depend on this frequency. But I'm going to simplify our life and assume that the range is so narrow and states are so similar to each other, and it is already a strong approximation, that the transition dipole doesn't change substantially. So in the limit of delta goes to 0, we can just take transition dipole at center of this distribution and assume that it will be very similar nearby. You can stop believing me from this point because it's a very strong approximation. Okay, and then we do reproduce sine squared. So if you feel bored and tired, I just want to remind the goal of this exercise is to receive a result that finally it will be a constant times t. Right? And constant will be rate of the process according to Fermi's golden rule. But we do try to get it in rigorous derivation, or as rigorous as possible with some approximations. Okay. Let's do another approximation. If you're already so reckless in admitting simplifications, let's go on next step and assume that if density of states changes in the vicinity of frequency, we can tell that density of omega is equals to Taylor expansion in point 0 plus derivative of density over energy times this omega lowercase minus omega uppercase. So it will be a correct way to proceed if you want big rigor. But for simple guys, we can assume that we are in a very narrow range where this derivative is negligible. So I'm going to migrate this density outside of the integral, just to make our life simpler. Probability that something will be excited at a given time is transition dipole convection field and constant density of the final states and the integral of minus delta plus delta. Let's discuss what is this epsilon, what is our integration variable. It's exactly this offset between frequencies of light and matter. And then we do have the sine squared, this difference So the goal is to prove that it will be proportional to time. If I try to apply intuitive imagination, I will not get it, at least how I think about it. So sine is in the limit. First order of Taylor decomposition of sine is t. Sine squared will be t squared. And then integration is not applied to the time, so it should be t squared, right? Or something unknown. But there are tricks that prove that this integral will give us will be linear in time rather than quadratic. So in order to complete this integration, we need to change variables. So we need to use new integration variable, which will be equal to this. So x equals omega. So everywhere where we do have something different, we need to practice mathematical liberty and multiply and divide. So 2x divided by t will be omega minus omega k1, right? So in the denominator, we should replace it by this expression. If you do have a derivative, then 2 divided by t are not changed, and then we have dx. Somewhere in transit, I swapped the sign, but since this function is symmetric, the result shouldn't be dependent. I admit it as a typo error, but I know that result will not change if you do it. So this is the substitution that we needs to go here. So probability that something will be excited. How dense are the states? Since we already admitted to put it outside of the integral, we don't bother to convert it into the variable, into the new variable. And inside, so derivative of this frequency difference is replaced by 2 divided by t dx. The denominator should be replaced by 1 divided by this factor, or we can swap it, so it will be t squared over 4x squared. I just release a little space, and then we do have sine squared of x. So did you catch any errors, or did you develop any suspicion? I just learned and memorized this and practiced over again this derivation, but it looks very suspicious to me. Intuitively, one expects to get t squared, and counterintuitive, one gets t. So if you didn't found any shortcomings or errors, so we cancel t here, squared there, right? And then we have a first power of time. This is the main result. The rest of things are important, but kind of secondary. So we get u e squared h bar squared density of final states. The integration is already going on. We inserted the integration into variable x, so we can put t outside, and then the rest is integral from minus delta to plus delta. 1/2 sine square x squared dx. And then we do have the answer as in light matter interaction squared, h bar squared, factor 2, density of final states. The integral, we will prove it after the break, will be equal pi, just constant pi, then times t. This is the result which is referred as Fermi's golden rule. Fermi's golden rule. Because it is so simple and it is applied, like we are working to apply it towards light to matter interaction, but to not any, very broad variety of processes, including collisions, nuclear reactions. One can take first order time-dependent perturbation theory, use just correction to Hamiltonian, right? And use some guess about density of final states. And in many cases, it generates the rate, or here we have a just population of final state that agrees very well with experiment. So it's therefore it's called golden, because it's instead of golden, one would use broadly applicable and often correct. So interaction, density of states, and then if you look for kinetics of population proportional to time, if you look for rate, we just take derivative of this probability and we'll get this stuff. Let's schedule a little break if you want, and reconvene back in like 5 minutes. Continuous gratefulness for your health. Did everyone return safely? No one lost in transit? Okay. There is a little trick that I do not feel comfortable believing in, but it's my duty to deliver it. So we did derive that we have a rate, we have a population that something is getting excited, right? And in this derivation, we did assume that at initial time, there was 100% probability of ground state being occupied. And instead of writing down probability of ground state occupied in exact expressions, we did replace it just by factor 1. Now there are some tricks that I consider cheesy, but they are everywhere. So it's my duty. So rate that something is getting occupied. Now, if we get the probability of the initial state that was originally occupied, it should be 1. That can be assumed as Eg of time equals 0, or Cg star Cg of time, right? Minus the population that has been transferred. If so, this perturbative correction, it all depends on an assumption. So perturbative correction promotes ground to excited. So it's implicitly has factor 1 there, which is population of the ground state, which is C ground star, C ground at time equals 0. Now, if we take derivative over time of the population of ground state, formally, we get this K. But if we think along that perturbation is not a standalone thing, it's just a rate of flicking from already populated pool to empty pool, there should be the instead of 1 of the fully populated ground state, we need to have the probability that ground state is populated at times is populated. At this here we practice this derivative in the limit of time goes to 0. If you want to carefully write down this expression more generally, then we should do it as dp ground of t dt minus equals minus k times p ground at time t. So I hate this logical path. If you, with me, you are okay to criticize it. But let's go forward and take it as a one more of assumptions and approximations. So the logic is that when we practice perturbation theory, we assume that something is already populated. We are just looking on transitions. So if we admit this trick, we can practice solving first order differential equation, right? What should we do? We should, if possible, put variables on different sides, right? D P ground over P ground equals minus K dt. So we'll get log of P ground equals 0 if you put limits, right? Initial and final equals minus KT. Now we can put the left and right sides to the power of exponential. So at the left, e to the power of this box, and to the right, we have e to the power of this box. Okay. And then exponential to the power of log will just reproduce whatever was argument of logarithm, right? So we put here probability that ground state is occupied at time t divided by probability that ground state is occupied at time 0. And then we can multiply left and right by initial population of the ground state. So we do get the, how do chemists call it? Something like zeroth order kinetics of reaction, right? So this exponential decay. Agree? So zeroth order kinetics of reaction is another application of Fermi's golden rule. Now you see how things are connecting to each other. There are potential, there are multiple applications where it works. And if you would have longer time for the course, it would be a time for more and more applications, like in homeworks, apply it to photo effect, to collision reactions, to something nuclear. So it's all possible and all works. But we need to go forward, and we will have expected and likely beautiful and outstanding talks from all participants on Thursday. They all talks are expected to be related to Fermi's golden rule. They are either preparation to Fermi's golden rule, or extension to higher order, or applications to Fermi's golden rule. So one of the subjects, I think, shared between bless you, not remembering exactly names, but one of the presentations is black body radiation, right? And in the black body radiation, one gets density of photon modes, which will be proportional to the frequency in the second power. One does get light to matter interaction, and in the situation of thermalized modes, one also get a factor of thermal occupation, Boltzmann factor that is in some sense artificially added to this expression, and then it gives the black body radiation. Another talk is on what to expect if it is higher order, right? The talk number 1 would establish bridge to our next chapter, when we would consider light to matter interaction on much longer time scales, going very far from the limit time equals to 0, and one needs to avoid any sources of numerical errors, which are predominantly contained in the simple processing of light to matter interaction. Okay, so I stay curious and open to assist in preparing and providing materials to talks if they need it, or need it more than already shared. And right now we need to, we are done with major things, but we need to practice this integral. So I'll probably go to the other board because this one, I don't know, maybe someone wants to glance on it for a longer time. And let me take the cheat sheet. If one looks online, there are about 6 proofs that this integral is equal to pi. But none of them are intuitive. They all are a little crazy. So I'm going to so plan is to convert this expression into the back into oscillatory exponentials. And so the major challenge is that we have the divergent denominator. What's the right word for mathematical for such? When things are like 1/0 that come to infinity.
Divergence, usually.
Divergence. Can one use the word pole?
Use what?
Pole, like North Pole, South Pole.
Yeah, I think so.
Okay, so it's there is divergence, there is a pole, and we need to somehow deal with it. So first, I'm going to convert this sine square into oscillatory exponentials, and then again, I don't know if you you'll be bored to listen to it. Let me ask who is comfortable with this integral and has an idea how to take it. I don't. I would fail without the cheat sheet, but maybe.
I mean, I could try stuff. I don't know what the correct approach would be.
But what would be
Those proofs you talked about before.
So I'll yeah, maybe it's time for a little interview. We have time. So what would be your strategy?
Well, what are our bounds of integration? So
Right now we have them very small, but we can for symmetry make them easy.
I mean, yeah, because if we're integrating across 0, we need to somehow get rid of that x squared on the bottom. I mean,
Okay.
we're gonna have to do that ultimately. Like,
We will do it. I promise.
that is an even function, so we could break up, like, if we're going negative infinity to infinity, we could just go 0 to infinity.
Okay. Okay.
I don't know.
Okay. Yeah. David, what would be your?
First thing I would do is again the function 0, because 0 is a big issue here.
Okay. Okay, yeah, thank you. Any other thoughts or ideas how to how to take it into account but avoid it? So in my time I didn't excel in complex calculus, but I have some blurry memories. So there are residue theorem. And there is these two keywords that help to take such integrals. And I don't know how to pronounce this Lorraine series. So if I would be like blanking in my mind in front of Google, I would look either to how to find this integral or just refresh memories on this concept. So sine x plus I x plus I x. I just do not remember trigonometric equations and going to reproduce them in a reverse engineering fashion. So sine squared x minus sine squared x plus I sine x sine x. X equals this one, sine x equals this one. Okay. I do not need this simple one, and we do have the equation for circle of radius 1. Now we can add or subtract. If we will add, it will be boring. If we will cosine here, we do need to subtract. Maybe minus cosine plus 1. So then we will get 1 minus cosine 2x equals, cosines will cancel, and then we'll have 2 sine square x. I didn't lie yet, right? So the goal is to replace sine square to some oscillatory exponentials for the following purpose. We may want to think out of box and jump from a linear integral along real line to extend towards complex plane. And then there are some tricks available. So sine square x can be replaced by 1 minus cosine 2x over 2. Originally we go from minus delta plus delta, but since all interesting things are in vicinity of x, going them to infinity is not going to affect result. So we are accumulating layers of approximations. One minus e to the power 2ix plus e to the power minus 2x divide, multiply by 2 here. No, not multiply, divide. So far, so good.
You should still have x squared denominator, right?
Yes, thank you. Okay. Now we can chop this integral on two terms. So this 1/2 can be considered as 2 times quarter, and we have 1/4 minus 1/4 e to ix divide x squared, and second integral minus infinity plus infinity dx 1/4 put outside of bracket 1 minus e minus 2i x.
Third no x squared on your first term.
Careful, careful. So at this point, I'm blanking. There is a thing that is assumed standard in complex analysis, and I will deliver it, but it's not inside myself. So maybe some of you who were recently taking complex calculus can admit it. So after taking the following approximation, the rest is just rolling down in simple logic and derivation. So if we assume that there is a real part of x and imaginary part of x.
That's another question.
Yes.
1 minus exponentials, shouldn't those be 2 minus exponentials? So it was 1/2.
Yes.
So it should be 4s.
Wait. If here we had 1/2, right?
Yeah.
And we want to share this 1/2 between two terms. So 1/4 for one term and another 1/4 for another one. So when we add them together, it will be 1/2. Yes.
You just take out 1/2, begin with, instead of begin to 1/4, you just put 1/2 on the outside.
Yep, it is possible. Finally, it will contribute nothing to the result.
I just think it would help with confusion with the 1/4.
So right now we are performing integration along the real line from minus infinity to infinity. The value of the expression under integral at distances far away from this special point, from this divergence from the pole, is negligible if we are on a big radius, right? So we can add or subtract. We can, instead of going integration along the line, we can assume that we are going integration along the closed path, along the contour, right? This I can admit. And next step that I do not admit, I have no choice to deliver it. They tell here it rolls forward, here it rolls backwards. Therefore, for the first integral, we will select the contour that will go counterclockwise. And for this one would select a contour that goes so same along the x-axis, but clockwise. So I admit taking this half circles and making it as a contour integral, but using different direction of circling for one and another integral looks very strange for me. I cannot justify it for myself. But if we admit it, then the rest looks much more logical. So next step. So there are more thinking and assumptions rather than straightforward derivations. When we perform our contours literally along the real axis, we will meet our special point. And if you go, it will give a divergence. Why don't we shift our contours slightly to the down? So I will keep the axis and redo this little dashes. So real axis, and the blue contour will go this way, below the special point. And the one that we agreed to use black will go also beyond special point. So this looks okay. What I do not get and do not agree with just selecting different contours for different signs of exponential. But if we admit this statement, then the next thing looks, I would say, even beautiful. So there are theorems telling that result of contour integration do have mathematical liberty of performing them. So instead of making this correct half circle contour, I can go something very curvilinear. And as soon as we cover the special point inside, the result will not change. So if we are provided with such liberty, right, then why don't we select a contour in a symmetric and pleasant way? So I'm going to erase this ugly contour and do a little bit better one. So if there is a liberty of selecting contour, real x, imaginary x, I can select a contour that corresponds to absolute value of x equals 1 and make it the circle of radius 1. So I'm converting this half circle to full circle of smaller radius. In some sense, this trick is similar to like Gauss and Stokes theorems in static electricity. So now we need to admit this, like if you accept this idea, then we need to express it mathematically. So a point in a complex plane that lay on a circle of radius 1. So typically one uses the letter z, but here is x, is equal to absolute value of x times e I phi, where phi goes from 0 to 2 pi. Right? So it's polar coordinate. We parameterize each point on the circle. So I'm going to apply this trick to the integral I plus. With your permission, I'm going to erase this part, and highly likely it will be enough space to complete everything. So if I expand the exponential into power series, so exponential in if zeroth order 1, first order is just the power of exponential 2ix. Next one will be higher order that we drop because it's too much to worry about. Then we do have we didn't convert it yet to the complex plane. Force integral 1 minus 1 cancels, and then we have 2ix divided by x squared plus higher order term. So series, when instead of powers of positive power, one has the powers of 1 over x, 1 over x squared, are called Lorentz series, and typically are used for the this complex plane integration. So the x is cancelled, right? And then we do have 1/4 dx 2I over x. So now it is time to combine this expression and this substitution. By the way, if we do a derivative of this, so dx will be x I e I phi d phi, right? If you take derivative over angle, which is our only parameter, right? And then we will get the I x d phi But our x is equal 1. We agreed it by the rule of the game. It is I e I phi d phi. So now it is time to plug it into here. Plus is replaced by 1/4 dx. Okay. You replace x by e to the power I phi, and we replace dx by I e I phi d phi. So this was x, this was dx. Now we have the integration in limits from 0 to 2 pi. Any errors? Any suspicion? So we replace integral along line by the integral along the circle, and circle is parameterized by only angle, right? So e to the I phi cancel, and then we get I times I will be minus 2 and 4 cancel 1/2, and then integral from 0 to 2 pi over d phi will be just 2 pi minus 0. And in transit through this derivation somewhere, I mistreated the minus sign. Yes, is in front of here, is in front of there, right? And therefore it should cancel here, right? Yes. No, not convincing. Okay. So we did prove that, and making this similar trick for the second contour will give 0 because one selects it to be below the special point, which I hate to admit, but it is how it is formulated. And the residue theorem is that contour integral around the special point can be computed by a special rule by like taking derivative of function multiplying by explaining going into Lorentz series, and basically it integral is equals to the number of special points inside of the contour multiplied by 2 pi. So if one would need to do something more complicated than this integral, one would use this definition. So integral from minus infinity to plus infinity of sine squared x squared dx is pi, and it is used towards the Fermi's golden rule. And all summaries of the Fermi's golden rule are there, right? So the population grows linearly, and with a little additional assumptions, Fermi's golden rule reproduces zeroth order kinetic. Yes, Tori?
That's for I plus, but we never solved for I minus.
I minus is was set up in such way that it makes a contour under special point, and by residue theorem it will be 0. And it is why I'm unhappy with this frivolous setting the contours. But as soon as we set it below, it immediately gives 0 along the integration. There are a couple of other ways to prove this integral, and they are a little less unnatural, but still not pleasant. Okay, I think we are done. Any questions are welcome, but if there are no questions, you're welcome to disconnect, depart, and looking forward to see those who are in class on Wednesday evening labs, those who are in research group in about 30 minutes and 40 in the conference room on the first floor.
Going over what we're going to be doing for the presentations on Wednesday. We'll be talking about the presentations for Thursday in lab on Wednesday.
We can, but I have program of running codes, discussion will be not the major such.
I probably won't be able to come tomorrow, or if I do, it'll be late.
That's okay, you either in person or online.
I'll make sure to watch it.
Okay, thank you.